Okay, welcome back. Welcome back. Yeah, there we go. So we know what we need to do today. That should be more on what we started last time. So today we'll discuss and finish our discussion on metric spaces. So we need to, we said a bunch of things about this. We just need to, we need to build up some interesting theorems. So last time we kind of proved why we cared about metric spaces. So those are pairs. Remember, this is a pair x comma d, where this d needs to satisfy some stuff. So we have three properties for this guy. Needs to be non-degenerate, symmetric, and triangle inequality. That's what you need for something to be a distance, like two-variable function with these properties. And then we saw when you have such thing, you get what's called a metric topology on X. So this was a theorem stating that this thing, which is going to be all subsets of X, for which whenever you have a point, you can cook up a ball inside of it. So that's the topology, all things, such that whenever you have a point on the set, you have a ball on the set. And here, of course, these balls, the balls, which is this set, x comma epsilon, where x can be any point, epsilon can be any positive number. These form a basis. That's by definition. We prove the theorem stating that this is basis for something, and this is the something that you get, this TD. And then something else I want to discuss today is on this R to the n for each p. For each p, let's say bigger than or equal to 1, we have a metric, dp, which is, well, dp of x comma y, which is compute all the differences, xi minus yy. These are all the coordinates. Do that to the pth power, sum from 1 to n is the number of coordinates, and do pth square root, pth root. Yep.
The topology alpha there,
Mhm.
how is that any different than the standard topology? Because you can define a multiple, right?
Well, to be completely honest, the difference is x is not the real numbers, and d is not that x minus y distance. So it's an arbitrary and abstract metric space. But then the idea is exactly the same. We have a new set with a new metric, but then the construction is absolutely the same. That's what we're kind of doing here. Yep.
Can you repeat? It was symmetric. It has the delta distance, and what was the third one?
Sorry, non-degeneracy.
Degeneracy.
Yeah, that's the definition from last time. Okay, so and then we also have the infinity distance. This is what you get when you let p go to infinite. You're just going to get the maximum of all these xi minus yi. And you are doing this for I between y and n. So this is mostly what we did last time. Examples, because we ended last time with a kind of definition of TD. So first example I want to discuss today is let's take a set. And we saw you can always define discrete metric or distance. So this is the distance from x to y. It's either going to be 0. That's the case when x is y. If x is y. And we want it to be 1 otherwise. So if it's called a discrete metric, the topology it induces. So I want to point here, sometimes this TD, it's called the metric topology, but most of the time you just say the induced topology, which is confusing because we use induced for subsets. But if there's no subset here and there is a metric, when you say the induced topology, you just mean the metric topology. Okay, so the topology induced by this distance, what do you think it's going to be? What are open balls here? If you center at X, what are open balls? That's kind of okay, but so the ball centered at X of radius epsilon, it's going to be either trivial in case epsilon is smaller than 1, or also trivial, but in the other sense, if epsilon is bigger than 1. So maybe I don't want to even say this. Then TD is going to be the discrete topology. And how do we prove such thing? So it's enough to show singletons are open. So singletons look like set with one element X is open in TD for every X. And if you show that, then your topology needs to be the entire power set. So how do we show that? That's true because the singleton is actually an open ball. It's the ball centered at X of radius anything smaller than or equal to 1. You can even put 1 here, but I will not because that could be confusing. I will use 1/2. And that's open. So the discrete metric, it's telling you on any set you can impose a metric. That's not very interesting. This one is not very interesting, at least from a topological point of view. Second example, on the set of the real numbers with a distance between 2 points given by absolute value of the difference. In this case, the metric topology coincides by definition, following the observation from before, with the standard topology. Because that's what we're doing here. Well, the standard topology is a topology coming from distance, from a metric, and coming from this particular one. Which, to be honest, is the only one that we have on when n is 1. These things just give you always the same one. Because you don't have a sum, you only have 1, and you're doing p, 1 minus p, so things cancel out, and this is the only one that you have. Yep.
When we do the discrete metric, X and Y, those are points, right? Those are sets, and those are lowercase x and y.
What's
E of x, y, right?
Mm-hmm.
That x and y are lowercase, right?
Yeah. Yeah, that's clear from what D is, function to variables in X. Any other questions?
The point to understand why you can pick between 0 and 1 for discrete topology radius of the ball.
You're saying why I have 1 here?
Yeah.
You can put anything here that's smaller than or equal to 1. Smaller than or equal to. So what this is telling you, you have your X here.
Yeah.
You have any other point? These are all points.
Yeah.
if you are different from x, anything different from x, when you compute the distance according to this metric, the distance is going to be 1 or bigger than 1, but always 1. So if you here say anything smaller than 1 or smaller than or equal to, the only thing that's in this set, so remember this is points in x for which the distance from x to y is, if I'm using 1/2, smaller than 1/2. Right? And no point different from x is a distance smaller than 1/2, only x.
Yeah, because that's equal to x, right?
Okay, third example. Here, I want to go to Rn, but I want to study this metric now, the infinity metric. So what are going to be the balls here between the ball center at some point x of radius epsilon? This is by definition points in Rn such that this max is smaller than epsilon, which means the distance from xi to ai is smaller than epsilon for every I. That's the only way for the maximum to be smaller than epsilon. You need each quantity to be smaller than epsilon. Right? But why satisfying this is just x1 needs to be something here. That's for x1, for y1, sorry. Y2 needs to live here. Blah, blah, blah. Yn needs to live here.
You're saying each of the y's have to be in those open balls. Right?
Open intervals, yeah. Open balls in the reals. Yep. And these are, well, in this case, squares, not rectangles or hypercubes or something. So open balls here, these are the basis for the product topology we consider on Rn. So the topology associated to this metric is just the product topology we consider. This is the only topology we consider thus far on Rn. So this is not really a new topology. We're just getting at it from a new perspective. So now the obvious question is, on Rn, for example, we have this family of metrics. The question is, if we have two metrics on the same space, so two metrics on the same set, induce the same topology. It's a, I will say, rather natural question to ask. Right? Each metric will give you topology. Maybe the topologies are the same. So let's try to say something about that. Here's our first definition for today. So far, what we're doing is just examples of things we know from before. We're trying to do new things now. So let's take two metrics. Let's call them D and D prime on the same set. So a set called X. So two metrics on a set X are called equivalent. So this is what I'm defining. If there exists two constants, C and C prime, in the open interval of the real numbers, such that. So what I want to say here is I want to be able to compare these distances just using scalars. And how do you write that? C times the distance from X to Y is smaller than or equal to distance prime, smaller than or equal to C prime distance from X to Y. And this needs to be true for any X, Y. So what I'm saying here is I can sandwich my new distance, D prime, between two multiples of the old distance T. Of course, you cannot pretend these constants to be like 1, because then also the distances are the same. And that's what we're doing. So something to note, some notes. The first one is, what this is saying is, I'm not saying this is trivial, but these inequalities, this means that, and this is kind of maybe confusing, but you can see it's true. If you compute the ball centered, well, I have different flavors for balls because we have two distances. But if you compute the D prime ball centered at some X of radius epsilon, we should be able to compare this with the ball centered, the D ball centered at X of radius epsilon. Somehow. But to compare this, I need to change the radius slightly using this one, using C. This is always going to be a subset of that one. And now, using this inequality, you can see this is a subset of D prime X C prime epsilon. So this looks confusing, but if you want to prove this, it's very easy. And this is for any X in X and every positive epsilon.
All on the left bigger. What is the C can be between all less than 1? What if it's bigger? What if C is bigger than 1? Isn't that a bigger ball?
I have D prime here and I have D.
Oh.
Yeah. This is kind of telling you there's something that's true here. This is kind of telling you C should be smaller than C prime. It's also kind of clear from this thing. But the important thing here is not the extremes. It's like the two consecutive inclusions. Yep.
Just to clarify, this is kind of like scaling in a way. Like on a more.
But instead of equal to, so scaling will be an instance of where this is true if you just put equals. But that's not, that's too much. Two metrics are pretty much never one multiple of the other. I mean, if you have a metric, you can rescale it and you'll get an equivalent metric. But rescaling a matrix is not that interesting. But yeah, in particular with this notion, we'll consider those kind of situations. So that's the first thing I want to note. Second one is, yeah, maybe need more space. Second one is, let me move the cameras. Ooh. Second thing I want to note, let's continue here, is if we are in that situation of the definition, we also have this thing. So you are sandwiching D prime between two Ds, but you also get like D prime, D sandwiched with two D primes. And you need to do this. This is going to be smaller than or equal to the distance from X to Y, which is going to be smaller than or equal to 1 over C. just like, for example, for this first one, you just rescale this inequality by C prime. And then for the second one, rescale this one by C and multiply by the inverse. So what I'm saying here is this definition is not really symmetric on D and D prime, but it is. You need to change the constants, and that's okay. So the last observation here is this defines an equivalence relation. On the set of all metrics. So here I'm saying two things are equivalent if blah, and it's easy to see using mostly this part that this defines an equivalence relation.
So what are some equivalence classes here? That's
Well, that's not an easy question. That's not an easy question by any means. Because we don't know what the set X is. We don't know what the possible metrics there are. But for example, now you have interesting questions. You have always the discrete metric. What's the equivalence class of that metric? That's a good question. You have all these metrics on Rn. Are all these guys equivalent? Those are interesting questions, but the partial questions that we can't even answer. So why do we care about this notion, proposition 2 for today? If we have two equivalent metrics, if D and D prime are equivalent metrics on the same set, of course, what do you think it's the theorem? Yeah. Right, they induce the same topology. Then TD is TD prime. But that's what I'm saying. Equivalent metrics induce the same topology. So let's try to prove this. Shouldn't do that. Let's try to prove this. What's going on? There we go. Sorry about that. Camera's doing weird things today. Probably the fire. I don't know. There we go. So let's try to prove this. So we want to show two inclusions, right? So we need to show two inclusions. So let's say we want to prove this one first. I don't know. So let's take some open in TD. Let's take something in TD. We have over there the definition for TD. And we want to show U is also in TD prime. And here I will write the definition of TD prime. I'm just going to rewrite that using D prime instead of D. The only TD that you have once you have D. Right? TD only depends on D. So I want to show U is in TD, which is, remember, the set of all, let's use V's now because U is used, subsets of X such that whenever you have a point, you always have an epsilon. And here, my balls, I need to say which ball it is because there's two distances, should be the D prime ball because I'm using TD prime. Right? So this is what we want to show. We want to show U is one of the subsets of X satisfying this. So we need to take an arbitrary X in U. Let's take an arbitrary element in U. And now we need to use that U is TD open. If that's the case, for some epsilon, there exists some possible epsilon, such that maybe I have epsilon here. Maybe let's change that for delta so that we don't get confused. It's just a variable. There exists an epsilon such that the entire TD ball centered at x of radius epsilon is inside that set U. But we want to show that for some possible different radius, the D prime ball is centered at U, is included in U. And of course, we're just going to use this. Using our second note here, the D prime ball C epsilon is inside that D ball, PT X epsilon is inside of U. So here, I'm not really saying what C and C prime are, but should be constants from this definition. Maybe I can write that. Before I start my proof, I should say, let C and C prime positive real numbers such that the distance prime from X to Y multiplied by C is smaller than the distance from X to Y, smaller than the other distance multiplied by C prime. Now I'm using that C over here.
C's exist, or we can just use them straight from the definition.
Oh, you know they exist from the definition. Yeah. So this is the first inclusion we wanted to prove. U is in TD prime. And to prove the other inclusion this way, very similar, but instead of using this, follow similarly. Of course, because this relation of being equivalent is symmetric. That's the point number 2 over there. Follow similarly, but now we need to use that the D ball center X epsilon C prime is inside the prime epsilon. So that should be an inverse. 1 over C prime epsilon. So I'm using this, but multiplying with the inverse here. And that's for any X and any epsilon. And that's the end of the proof. Any questions?
This works for like any abstract X.
Right, for any set X and any 2 distances which satisfy these. Let's be honest, very strong thing. It's a very strong relation.
For example, where that doesn't work, C and C prime.
So 2 metrics which are not equivalent? That's a very good question. And of course there is. Examples. Maybe let's start to begin with a non-example. So 1 is non-example. Let's just use probably the real numbers. Right, here we have the standard topology and we have the discrete topology, for example. We know these 2 are metric topologies, but they are not the same. So the distances cannot be equivalent. We have discrete topology. and which is not the standard topology. And as a consequence of this theorem, or the contrapositive, hence the discrete metric on R is not equivalent to the standard metric, or Euclidean metric. D of xy is x minus y absolute value. So I'm not even proving these two things don't exist, which you can do by hand, and I'm just using my theorem. And I have to switch colors because otherwise I'll have to refill this now. So let's switch to blue now. That's the first non-example. And another non-example, this will be part of next homework assignment. So I want to say the converse of this statement. So to be honest, we start this with this question. And I'm not really answering this question, because I'm not saying if you want to answer a question like this, you need to go if and only if. Right? So here I'm saying, in this particular case, the topologies are the same, but the converse is not true. It's not true in general. I mean the converse of this proposition 2. And it fits kind of spectacularly. So suppose we have a metric space. So suppose we have a metric space. And now we define a new metric. Well, to be honest, we only define a new function, d prime of xy is going to be d of xy, but I'm normalizing it not by a number, but I'm being more smart than that. Then this can be shown to be a metric. It's not trivial, it's a computation. Then define this. It's also metric. That's going to be part of homework. So notice, by the way, this is always smaller than or equal to 1. Because I'm dividing this thing by this number that's bigger than this guy. It's also metric. You can prove that. You can also prove, so everything that I'm stating now will be part of homework, which is not equivalent to D mostly because I'm kind of normalizing by different constants. Not equivalent to D, but induce the same topology. So in general, sometimes it is equivalent. In particular, it can be equivalent when D is the trivial metric, the discrete one. It's not equivalent to D, but induce the same topology. So that's a nice example. Are there any questions about that? Well, I'm just defining a new metric. And I'm telling you these metrics are not equivalent, but that's something that needs to be proved. And that's what. Right, you can show that the definition is never true for any C and C prime. So yeah, those constants cannot exist. That's what you need to prove. Well, that's another homework question. Yeah, you will know that when you start doing the next homework assignment. But the idea is
kind of strange that it's not.
Could be, yeah, could be strange. Yeah, probably I don't want to say much, but the thing is, balls are still related. That's what's going on here. Yep.
What does it say? Define D is looking at undeffined X blah, 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 is also a metric on X, which is not equivalent to. What is that?
B.
D is gonna.
Okay. No, so these are mostly non-examples of the proposition. So probably shouldn't be called examples, but kind of examples of the contrary. Now what I want to do is I actually want to use the theorem. And there is one space or one set where we have several different topologies. And that one is R to the n, well, different metrics, sorry. So we want to apply this to R to the n. So on X, which is R to the n, remember we have metrics dp, and this is for any p bigger than or equal to 1. Maybe let's say we have dp where p is something between 1, including infinite. And we can show, so this is, the thing with equivalent metrics is once you have the statement, it's easy to prove. So one can show the following for any pair of points, x comma y in Rn. You can compare all the metrics to this one. The infinity of xy is going to be smaller than or equal to dp of xy, which is going to be smaller than or equal to n, that's the number of variables, to the 1 over p dp. No, this should be the other one. That's for any p. And since this is an equivalence relation, all the dp's are equivalent. In particular, they are equivalent to either the infinite, which is the one with the product topology, or D2, which is the one with the standard topology, the Euclidean topology of Rn. So we know these dp's are not giving us any new topologies. Hence, they all induce the same topology. And the reason behind this is something like, if you compute, so I will not be precise with radius here. If you compute a D2 ball, it's going to look like that. And for example, the infinite ball is always a square. And then, of course, you can sandwich them. That's kind of what we're saying. But since this is an equivalence relation, and now you come up with a third one, don't really know what the shape is going to look like, you can sandwich them however you want. So let's say this is some dp. So that's the reason why all these guys will induce the same topology, and everything here is centered at some x. Yep.
Okay, I get the first one, the first ball being a square, but how do you get the second one as a circle? D2.
So in D2, when you compute D2 of x comma y, it's the Euclidean topology. So square root of x1 minus y1 squared plus x2 minus y2 squared.
So then once you go past the second square, then it could be any shape, like if you generalize it.
Well, it's not really any shape. They're usually like ellipses, but it's not something I want to focus too much now because I could, but I know they are all going to give me the same topology. So maybe we shouldn't. But I want to say, knowing that you can consider the topology either using open squares as bases or open circles as bases are very useful things. These two shapes are very useful. And you can play with whatever you want because they are different bases for the same topology. That's what we're saying here. Open balls form a basis for the metric topology, and we're saying the topology is the same. So what you're having is different shapes of open balls. These are open balls regarding different metrics. They're going to give you the same topology. And the reason is you can sandwich them. Well, I just erased that.
Is in that picture?
It's
assumed to be bigger? The two.
No. You can always. Now I'm just saying here we have. Probably I should say this is the infinite. We have the infinite. This is also the infinite. And we have more norms, dp for any other p. But usually we will not use them. You can. But this theorem is telling you you don't need all of them. You only need one. And I'm telling you, usually you don't really know which one you want to use, of D2 or the infinite. That depends on the setting. Sometimes you want to have squares for your arguments. Sometimes you want circles. Yep.
Does that mean we can like interchange the metrics like anytime we want?
Yep. All the metrics are going to give you the same topology. Now, if you have a question about the metric, you cannot change the metric. But if you have a question about the topology, you can. So yeah, let's write this as an example. What I'm trying to illustrate here is how I want to raise this. How are we doing with time? Okay, let's try to write this. So as an application of this, what I mean by sometimes you want to use different metrics, recall we have S1, the unit circle, inside R2 with the induced topology. And here, so this is our S1. Here's our S1. And some time ago, we were discussing that function. So this is our S1. And there was a function from, maybe one more space. There was a function from 0, 1 to S1 called that F. That was like going around the circle. And I claimed this F, so F of t is not a suspicious thing, is cosine of 2 pi t, sine of 2 pi t. So this function is, let's say, this is F going out of 0, 1, open at 1 to S1. So this is continuous bijective function. But not open. Not open. Open is coming from homework. Because if you take this guy here, let's go from 0 to 1 over 4. The image of that guy is going to give you this set. And this guy, f of u, if this is u, which is 0, 1/4, f of u is going to be point in S1. Here we want y to be bigger than or equal to 0, right? And x to be positive. It's not open. This is open, but this is not open in S1. And the reason is because here we have this point, because this is not the neighborhood, of the point, this point, 1, 0. And why that's the case? Because using this, D2, or also the infinite, but it's easier with the infinite, any interval of D2 of this guy will have negative y's. Any neighborhood of 1, 0 contains something like, let's call it 1 minus epsilon, 1 plus epsilon, times 0 minus epsilon, 0 plus epsilon. And this is problematic, have negative values, and that's not the case here. Yep.
That explanation makes sense, but what makes sense if you were to have, or to me, what makes sense is that if you were to somehow have, if you had to make that neighborhood argument on the number line, right, it's from 0 to 1 to 4, couldn't you make the same argument because 0 is inclusive? Could you make an argument that any neighborhood around 0?
You mean open at 0?
Yeah.
Yeah, that the image of that set will be open. If you do open here at 0, the image will be open.
Yeah, but what's saying is not even just the circle aspect, but like if you were to map 0 closed to 1/4 open to another, let's say it's from R1 to R1, right?
No, I don't see what you're saying. What's R1?
What's saying like another number line, right? That goes from 0.
Another?
Like instead of mapping it to a circle, you map it just to another.
Oh yeah, if it's another example, maybe we should discuss it afterwards. But is this example okay?
It's the fact that it's closed at 0. That's the issue.
Right, that's the issue. But you don't get to go any lower than 0. You have 0, but nothing smaller than that.
So that was open, then we will be open. The image will be open.
The image will not be open because it's not a neighborhood of that.
If 0 was open, then we're open at 0.
Oh yeah, if you take 0 open here, yeah. Yep. But if we're claiming the function it's not open, it's enough to find one open for which the image is not open. And this one is the one that's going to work. Probably the only one. Something like starting close at 0. Okay. So last 10 minutes, I want to prove another proposition, which is kind of, if you remember when we first discussed what a continuous function should be, I said something like, well, let's start with the analysis epsilon delta definition. And then we have like balls. And then I said, well, now in general topological space, those balls should be neighborhoods because we don't really have balls. What we have is neighborhoods. But now we do have balls. So we need to address how these things work, how these two things work. So here's the last proposition for today. I think it's number 3. Let's take two metric spaces, x distance on x and y distance on y. And let's take a function. And let's fix some a in x. Then the following are equivalent. The first one is f is continuous at A. And two, for every epsilon, there exists some delta such that if you are close to A, that should be delta. If you're close to A, then F will map you to something close to f of A. So this is the usual analysis definition. So what we're saying here is something like distance from A to X smaller than delta, then distance from f of A to f of X smaller than epsilon. This is what we're saying with this inclusion. And of course, I have two different distances here. This is distance in X, and this is distance in Y. So here I should say probably Bx and By, or B dx and B dy.
Even like subscript, subscript.
Right. If I'm being completely rigorous, I should say B dx and here B dy. That's the notation I used because I'm calling this dx and dy. So this is exactly what we're saying here. So let's try to prove this. Proof. Let's prove 1 implies 2. Maybe first one I want to say is, when do we say f is continuous at A? Because we didn't really use that a lot. So this means, let's assume f is continuous at A. And I will write what that means. Assume f continuous at A. What this means is, hence, for each neighborhood, let's call it U of f of A in Y. There exists some neighborhood of A, B neighborhood of A in X. That's going to be mapped to U, into U. F of U is a subset of B. Oh, wait. Other way around. F of E, subset of U. That's the definition of continuity at A. So now this is independent of the metrics. This is just a topological statement. Now we want to show this. We want to prove 2. So we need to take an arbitrary epsilon. And what can we do with this epsilon? Well, we need to focus on this ball, right? Of course, this ball is just the neighborhood of f of A. And this ball, f of A radius epsilon, is a neighborhood of f of A. Now, by continuity, at A, there exists some neighborhood U of A in X such that f of U is a subset of I should call this V again, sorry. There is a neighborhood V such that f of V is a subset of this one. We probably should call this Q. It's a neighborhood of this one. Just using the definition. Now, we're not done because we don't know if V is an open ball. We just know V is a neighborhood of A, but we don't know if it's an open ball center at A. What can we do about that? Yeah, we need to use the metric. So what we have at this point is, here's our V. Here's our V. It's a neighborhood of A, so it's not necessarily open, but it contains something open here. So it contains something open, and it's going to be mapped into our ball. This V here, f of A epsilon. So here's f of A. Here's epsilon. So V might not be open, might not be a ball, but we can write what the definition of neighborhood is. If it's a neighborhood, there exists some open V prime, open in X, T dx, such that I'm trying to picture this one here. So A is in V prime is a subset of V. So here's my V prime. Right, that will be the global definition of TDX, but I can also use the local one. If you are open in dx and you contain A, my definition of TDX, right, if you have A, since A is in B prime, which is inside of B, there exists some open ball containing A inside B prime. There exists some open ball, so that's some delta. The open ball center at A, radius delta, is inside of B prime. That's the delta. So what I'm doing here is I have my B open ball. Here's my ball, A delta. And now since the entire B lands inside this ball, of course, this subset given by the open ball will also land inside of that. And since the ball here, A delta is inside B prime, which is inside of B, what we have when you apply F to the ball, you will be inside of F of V, which is inside this ball. And the converse implication will be an exercise for you. So 2 implies 1 is an exercise. I want to say most of these arguments can be just reversed. Not entirely, but for most, mostly can be reversed. And let's stop here.